you can see that there is a Lee final from 2021 and also the solutions. And if you look at them right there. No, definitely not. I would say it's probably not super similar to Tav's final. That said, there's probably still some good practice on there. So for those of you in Tav's class, I would say you're welcome to take a look at this. And here's the exam written in like a way where you don't have a lot of space, but then the solutions over here. Definitely look at the problems, and if one of them looks like it might just be way out of this world, skip it. If you're looking for more practice. So there's Lee's final from a couple years ago. I will say Lee's final was not easy. Like I was writing solutions and there were a couple problems, specifically problem 3A was the 3A wasn't bad, sorry. It was one of the improper ones. Partial fractions were all right. The first improper one was all right. The second improper one, problem 4B, seemed extra challenging to me. So there was an integration by parts, and then you had some limits that were terrible that would have normally required the use of L'Hopital's rule, which I know is something that's not necessarily in your wheelhouse. So yeah, that was the only problem that was really terrible on Lee's practice final or actual final he gave 3 years ago. Yeah, so anyway, that's there. It's a good practice. We want more practice. That said, I do intend to write a final for practice final for Tavernetti, mimicking the one he's already written. It's going to be a minute though, because I need to write a practice final for another class before yours, because their final is on Tuesday and yours is on Thursday. So theirs needs to get written first. So I got to do that first, and then I'll try to do that. I intend to get it done no later than Monday of finals week. So I think that's a reasonable amount of time to still have a chance to look at it and practice and do whatever. Yeah, for those of you just coming in, here's the attendance thing. I'll scan. You need to scan it fast. So yeah, so that's on there on Canvas. Cool. Yep. Right. And it's a fine exam. It seems a little hard in my opinion, but that's my opinion. And then sure. So my plan today, as I mentioned last time, is to kind of go over just the kind of things you need to know. And then if you want, we can do some practice problems of various types. And again, if you have come with questions, great, we can do those, or I can just start picking and choosing. Might need something to write with though. Okay, so let's go through the things we need to know. Yeah, everything. Co-16B. Today is Pi Day of all days. Right, 3.14 Pi Day. Also Einstein's birthday. Is there a bug that needs killing? Or not killing? Yeah. You're welcome to do whatever you want with that, as long as you keep it away from me. They're not, I don't think they do, like they don't bite. They're perfectly fine. Oh yeah. If it was a mosquito, I'd say kill it with fire, but it's just or actually no, if it was a wasp, I'd say kill it with fire, because wasps, not a fan of wasps. But try not to kill the bugs unless I really feel like I need to. Okay, so things we need to know. I'm going very general here. If you know that something's not going to occur on your final because your teacher has said so, obviously you can ignore that. So I would say first the derivatives of the exponential and logarithmic things. So you should definitely know, and I'm going to kind of write the most general version of the formula. So what I would say here is I like to write stuff, but I'll use the letter U instead because that's a very normal thing. So we're going to say that U is our stuff. So we know that the derivative, I don't even think I need to write the e to the x version. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's the very book way of writing it. And then the derivative of a to the stuff, where a is a different base, like 2 or 3 or 7, same formula. It's going to be a to the stuff times the derivative of the stuff. Then we have to tack on a multiplication by the natural log of your different base. I will point out, as I pointed out before, technically we could have written that up here as well. We could have multiplied by a natural log of e, but that's just one, so we don't write it. And then on the other side of things, and the other side just mean like the inverse function, the derivative of the natural log of some stuff. I always write it as 1 over the stuff times the derivative of the stuff, but most people like to write it as one, like the derivative on top of the stuff, which is also fine. 1 over the stuff times the derivative of your stuff. And then if your base is different, if you have the derivative of, say, log base a of some stuff, it's going to be 1 over u times the derivative of your stuff times 1 over the natural log of your base. And again, you could probably compactify. You could, there's a better word for compactify. You can make this smaller. You can make it look more compact. Not write it out the long way that I have done, but that's what we got. And then I will say the other kind of differentiation thing we learned about exponentials and logs is the process of logarithmic differentiation. So, and I think this is really just best done by example. So let's do an example. So the logarithmic differentiation, where you have something like y equal to some, I'll write, actually I will write it kind of generally here. So if you have y equal to a function of x to a power that's also a function of x. So for example, you have y equal to, say, let's make this not too terrible, sine of x to the x squared plus 1. If that's the kind of function you have, then we take the natural log of both sides, we bring the power down, we differentiate both sides, and then we solve for y prime. So that's the very general process. We take the natural log of both sides. So you get the natural log of y equal to the natural log of sine of x to the x squared plus 1. We bring the x squared plus 1 down in front. So you have the natural log of y equal to x squared plus 1 times the natural log of sine of x. Then we differentiate both sides, and we have to, almost always have to use the product rule on the right-hand side. Maybe more rules as well, but certainly the product rule is going to come up. So taking the derivative of both sides, oh, and on the left-hand side, the derivative of the natural log of y is going to be 1 over our stuff times the derivative of our stuff. 1 over y times dy dx. The right-hand side, hopefully I have myself enough room here. The derivative of x squared plus 1 is 2x multiplied by the natural log of sine of x. And then we add and we flip it. We leave the x squared plus 1 alone. And then I'm going to try and save myself some space here. Instead of writing 1 over the stuff times the derivative of the stuff, I'm going to write the derivative of the stuff on top. So it's going to be 1 over sine times the derivative of sine, which is cosine, which I'm going to write as cosine of x over sine of x. And I really, really think you can do this last part in one shot. You're going to multiply both sides by y, and also replace y with the fact that y is equal to sine of x to the x squared plus 1. So we're going to get dy dx equal to, watch for a second, y, there's my y, times all that. And I would do mild simplification here, right? This is 2x times natural log of sine of x plus x squared plus 1 times cosine over sine is also known as cotangent of x. Not required, but I would write it that way because I would. But if you left it as cosine over sine, that would probably be fine as well. But again, right, I'm doing two things at once. I'm multiplying both sides by y, you get the y over there, and then replacing y with what y is equal to. And that's our answer. I can't imagine there won't be a question like this on Lee's final and Tab's final. Like, it just seems very likely to me. Not a guarantee, just my opinion. I suppose I don't really have to say that. You know that. You know that, right? Nothing I say here is for sure. Everything is what I think is going to happen, but I don't actually know. All right. I feel like that's, oh, and then there's exponential growth and decay. Yeah. Yeah. So exponential growth and decay. Yeah.
Instead of writing du dx, could you do like u prime?
Yeah, totally. Yeah, 100%. Yes. Yeah. All those du dx's up there, you could have written this as e to the u times u prime. This could have been a to the u times u prime times natural log of a. This could have been 1 over u times u prime, or if you really like, u prime over u, and this could have been the same thing, 1 over u times u prime times 1 over natural log of a, or if you really want to write it in a more compact way, u prime over u times natural log of a. Yeah, all that's prime or d, whatever, either one is usually very acceptable. There are some instances where we really prefer one because of reasons. Mostly I would say we often prefer the Leibniz notation, the dy dx notation when we're doing related rates. That was 16a. So I don't think, oh, and then when you like kind of solve the differential equation by like, you'll see this in 16c, when you're trying to solve a differential equation using a process called separation of variables. You really want to write dy dx or whatever you have so that you can think of like multiplying both sides by dx to get the dx's on one side and the dy's on the other side. But that's next quarter, if you're taking it. Cool. Okay, so yeah, exponential growth and decay. What do I have to say about that? I would say, so typically your model for exponential growth and decay is y equal to c e to the kt. And usually when you're doing exponential growth and decay problems, it's mostly just you're given some data points and asked to find something else later. So again, giving an example, because it's really kind of weird to do a problem like this without giving an example. I could say we have some, sure. So for example, some radioactive material. And we know that at the beginning, or I should say initially is maybe a better word to use there instead of at the beginning, we have 26 grams. And 3 hours later, we have, how do I have a thought here. No, yeah. We have 20 grams. So I've given you 2 data points, right? I've given you the amount at some initial time and the amount at some later time. And then the question often is, how much do we have at a later time? Or what time is it later when we have so much? So we could ask the question like, how long until only 10 grams remain? Or I could ask the question, which is more stereotypical, which is what is the half-life? That question is the same sort of question, just phrased differently. What is the half-life question is really just how long until there are 13 grams left in this particular example, or half of the original amount more generally. But I'll ask it differently just to make it interesting. So if I was doing this problem, here's what I would do. I would write my model, y equals c to the kt, and then I really think it's very helpful to write this little table of times and amounts. In the beginning, there were 26 grams. And then 3 hours later, there were 20 grams. And then some number of hours later, which we're trying to find, there will be 10 grams. So first we're going to use these first 2 data points to find C and K. And then we'll use the last unknown to solve for what we're trying to figure out. So here we would say, great. So again, I think you can skip this step and just say, yeah, we know that y is going to be 26. It's equal to c e to the k times 0. E to the 0 is 1. C times 1 is c. You get c equal to 26. That c value there is your initial value at time 0. Occasionally, someone's going to give you a problem where your times are both not time 0. They might say, like, you have some initial number of cells, and then 3 hours later you have 500, and then 5 hours later you have 800, and then they ask you, like, how many did you start with? And that's kind of a different animal. I don't think that's going to come up on your final. Again, I don't know. Usually we have this sort of situation. Then we use the other data point along with this c value to figure out what k is. So we're going to plug in 20 for y, and 26 for c, and 3 for t. And then we solve for k. Divide both sides by 26. Take the natural log of both sides. I would reduce this fraction to 10/13. So natural log of 10/13 equals 3k. Divide both sides by 3. 1/3 natural log of 10/13 is equal to k. And then we say, great, our full model is given by y equal to this c value of 26 times e to the that k 1/3 natural log of 10/13 times t. And then finally, we're going to set y equal to 10 and solve for t. So we're going to have 10 equal to 26 e to the garbage times t. Ooh, I wrote that e in a weird spot. I wrote that as an exponent. That is not good. Try that again. We have 10 equal to 26 times e to the garbage times t. 1/3 natural log of 10/13 t. And then solving for t here is very, very similar to how we just solved for k. We get rid of the coefficient of e by dividing both sides by 26. So 10 over 26 is equal to e to the 1/3 natural log of 10/13 t. And then we take the natural log of both sides. So we get the natural log of 10/26 reduces to 5/13 equal to the natural log of e to the stuff is just the stuff. And finally, solve for t by multiplying both sides by 3 and dividing both sides by 10/13. And if you're given a natural log of 10/13, apologize. And typically your answers for these kind of questions are gross. Occasionally, I will point out one more thing here. Occasionally someone will give you a problem that is somewhat nice, or at least maybe not nice, but they want you to think about it in a nice way. For example, on Lee's practice or actual final, he gave the following question. Let me actually go. Oops, sorry. So the question was basically, what was the question? Let me go look real quick so I remember exactly what it is and not try to make it up here. Sorry, one sec. Co-16B. So the problem he gave was I think this one's kind of interesting. Yeah. So in a research experiment, a population of fruit flies grows exponentially. The population. The only reason we're saying that is so that you know that you have the usual sort of situation. Y equals c to the kt. Although we're not actually going to use it here. So here's what then we're given. After 2 days, there are 50 fruit flies. After 4 days, there are 100. And then the question is, I'm gonna ask you this. I'm gonna ask a different question. The question I'm gonna ask is, how many will there be after 10 days? And follow-up question, how many did we start with? Okay, really, really important feature of exponential growth and decay is that the amount of time it takes for a population to multiply by the same factor is constant. So we know that it takes 2 days for the population to do what? Right, double. So every 2 days, the population doubles. So what we can say, and I like my little table here. If time equals 2, the population's 50. If time equals 4, the population's 100. If time equals what, the population is going to be 200. What's the next time I need to get another doubling? Not 8. So the time amounts are constant intervals. So the amount of time it was from 2 to 4 is 2 days, and it has to be that amount again. Another 2 days gets me to day 6, where the population's 200. Another 2 days is going to get me to day 8, where the population should be how many? And then finally, 2 more days gets me to day 10, where the population should be 800. So every set amount of time multiplies the amount by the same factor. It could be a doubling, it could be a tripling, it could be whatever they've kind of. So like if I had rewritten this problem and said on day 2 we have 50 and on day 4 we have 150, then we're tripling every 2 days. So then on day 6 we'd have 450, which is 3 times 150, and so on and so on. So the length of time being constant intervals means the population multiplies by the same factor every time. Okay, follow up. How many fruit flies do I have to start with? Right, because it's doubling every time, every 2 day interval, and that's another 2 day interval, but we just went backwards. So instead of doubling, we halved. Cool, I like that problem. It's kind of good. So this problem was asked on his exam, and I don't think he wanted you to do any of this on Lee's exam, this y equal to CE to the KT stuff. I really think this is what he intended for you to see, was that you're supposed to know with exponential growth, constant time intervals, you have the same multiplication factor for your population. Okay, let's see, where was I? I was looking at that. Yes. Okay, cool. I think that's most of, yeah. So that's all the derivative stuff I think we need to be aware of. Again, and more the not integral stuff we need to be aware of. And then the rest of it's integrals, integrals, integrals. So the rest is all the integral stuff. Yeah, lots of things to say here. So first, I'll just point out, yeah, let's talk about kind of application stuff before we talk about methods. So area under a curve. Here's the picture I'm thinking of. We got some curve f of x from A to B is just the integral from A to B of f of x dx. Area between two curves. Maybe you have something that looks more like this now. You've got some g of x and some f of x. And they intersect at x equal to a and x equal to b. That's going to be the integral from a to b of the top function, in this case g of x, minus the bottom function, in this case f of x. I should be more explicit. The top function over the interval minus the bottom function over the interval. Outside of between a and b, actually f of x is on top and g of x is on the bottom, but that doesn't matter. We only care about between a and b in this thing. A couple other notes here. Typically, we find the values of a and b by setting the functions equal to each other. And solving. Occasionally you get more than 2 points of intersection. I'll also say that the way you figure out which functions on top, if they're hard to graph. So if graphing isn't an option, or if graphing is too hard, pick a number between A and B. And then if, let's call it C. If g of c is greater than f of c, then g is the bigger function. And g of x is bigger over the entire interval. And likewise, I'm not going to write it down because I think it's obvious. If f of c is bigger than g of c, then f of x is the bigger function over the interval. So that's how you can figure out which one's bigger without having to graph the whole thing. Let's see. Did we talk about average value?
that a thing we did at some point? Okay. It's not that big a deal, but I should write it down. Two more kind of application things, which are average value. So the average value or the average height of a function on some interval is really kind of the easiest thing you could ever, I mean, it's the easiest extra thing other than just calculating the interval. It's going to be the integral from a to b of your function divided by b minus a, or sometimes people write it as 1 over b minus a times the integral. Either way, it's fine. You're just taking your area, dividing by the length to get the average height. And lastly, we do have the disk and washer method for volumes of revolution. Remind me, I think in Tav's class, you only ever rotated around the x-axis. Don't think there was ever any horizontal rotation or rotation about a different, excuse me, around a different line, like y equals 3 or y equals -2. So I think instead of trying to write these formulas, it's better just to do a couple of examples. Let's do 2 examples of volumes of revolution. One will be a disk method, one will be a washer method. So first, let's find, try not to write all the words here. So we're going to find the volume of the solid obtained by revolving the region bounded by, let's not make it too terrible, James. Sure, by y equal to the square root of x, y equal to 0, and x equal to 9 about the x-axis. These problems are times when I do think you want to draw the region if you're capable of doing so. So I'm going to draw my 3 functions here. Functions probably too strong word. My 3 graphs here. So y equal to the square root of x is the usual square root shape. Y equals 0 is which axis? Is it the y-axis or is it the x-axis? The x-axis. Great. I don't really want to draw it again. There it is. And then finally, x equals 9 is a vertical line like this. So great. I can see the region that is enclosed by those 3 functions or those 3 graphs. It's this stuff right here. And notably, you can say this one of 2 ways. The region is flush with the axis of rotation. Or if you prefer, the axis of rotation is one of the boundaries of my region. Either one of those statements means that we need to be using the disk method. Or in other words, when you rotate this thing around, you're not going to have some middle part missing. You're just going to get some solid thing without like some cutout part in the middle. So rotating this around, I'm thinking about taking this little strip here. And when I rotate that strip around, I get a disk. Again, you don't need to draw this picture. I'm just drawing it to remind you of what's happening. And the volume of that disk, well, if I call this the radius of the disk, then the volume of this disk is pi times the radius squared times the thickness, which is a small change in x, which I like to call dx. Some people call it delta x. Either way is fine. Then the total volume is going to be, we're going to add up all these slices, all these disks. So our total volume is going to be the integral from as far left as x equals 0 to as far right as x equals 9 of pi times my radius. But my radius, actually, I probably should have done this before, but fine. My radius here is the height of that strip. It's the top minus the bottom, which is the square root of x minus 0. My radius is just the square root of x. Because it varies, right? if x is 1, my radius is just 1. If x is 4, my radius is 2. If x is right, if you move from left to right, the radius gets larger and larger and larger. So that's what we'd be having to integrate. This one's pretty straightforward. I think we should do it. But I will point out, a lot of the time for volumes especially, they will ask you to set up and not integrate. So read the instructions carefully. Don't be integrating stuff that you're not going to get points for integrating. So then this is going to be pi times the integral from 0 to 9 of x. We're going to get pi times x squared over 2 from 0 to 9. We're going to plug in 9. We're going to get pi times 81 over 2. I'm not even going to plug in 0 because I know I get 0 when I do. That doesn't always happen, but it happens here. So I would leave it like this or write it as 81 pi over 2. Cool. That was a disk method example where you didn't have an inner function that you were kind of subtracting out. Let's look at a different example. Let's say same idea. Volume of the solid obtained by revolving the graph or the region bounded by. I'm just going to start with the bounded by part because I don't want to write all that again. Bounded by, or what have I got here? Let's see. Good call. Let's say y equal to x squared and y equal to, yeah, sure, 6x. Why not? Before I can start graphing these things, and not that I couldn't graph them right away. I mean, sure, we can graph them. Y equals x squared is a pretty straightforward graph. It's just your usual parabola. And y equal to 6x is a straight line with a pretty steep slope. We don't have to draw it super steep. It does go through the origin. Something like this. So I probably should find those points of intersection. It seems obvious that the origin is a point of intersection here. Let's find both of them though. So if we set x squared equal to 6x, even though it feels convenient, I would not recommend dividing both sides by x. I would bring everything to one side and then factor out an x to get x equal to 0 and x equal to 6. But I will point out, if you can just see that x equal to 6 is going to be the other solution here, because you can imagine dividing both sides by x and then getting x equal to 6, that's also fine. No one's really checking your work to see how you got the limits of integration unless they were wrong. So that's the point 6, comma 36. There's the point 0, comma 0. So now, when we take our little vertical strip and rotate it around the x-axis, we don't just get a disk, we get a washer because we are missing the middle part. So we have an outer radius and an inner radius. And the volume of our disk is going to be the volume of the outer disk minus the volume of the inner disk, or essentially the area of the big circle minus the area of the little circle, all times the thickness of the disk. So pi times big R squared minus pi times little r squared, all times dx. In this case, our big radius is, our graph shows us that the straight line is the further away thing. But let's pretend like we didn't graph it, even though I think it's a terrible choice. If we didn't graph it, and we knew that they intersected at 0 and 6, pick any number between 0 and 6. Don't pick any number. Pick the easiest number between 0 and 6. What's the easiest number in my opinion? Good question. What is the easiest number to plug into something if I have to pick between 0 and 6? 1. I would definitely pick 1. You can pick 2 or 3 or 4 or 5, but 1 is probably the easiest thing to plug in. If we do it, if we plug in 1, we're going to get y equal to 1 versus y equal to 6. So that's clearly the bigger one. So the line is the bigger function. The line is the bigger radius. So that's going to be pi times, let's factor out the pi. Pi times 6x squared minus, then the smaller radius is x squared. Yes. So if we're going to calculate the total volume, we're going to do the integral from as far left as 0 to as far right as 6. Pull out the pi, and it's going to be 6x quantity squared minus x squared dx. And then the rest is not too terrible. It's pi times the integral from 0 to 6 of 36x squared minus x to the fourth. That's going to be pi times the integral from, not the integral, I'm going to do the integration here, sorry. The integral is 36x cubed over 3, which does reduce to 12x cubed minus x to the fifth over 5. Then I have a plug in 6, and I'm going to get pi times 12 times 6 cubed minus 6 to the fifth over 5. Minus 0, minus 0. I don't think you should bother simplifying this unless you've done everything else you possibly can on the exam and you're really, really bored and you feel like doing some calculations. Or in other words, don't simplify this unless you were asked to. Don't lose points simplifying something that you're not asked to simplify. Unless it's something that's super obvious, you're like, I can't help myself. Like there was one a minute ago where I was like, I have to simplify that because I just can't not. Okay, so those are like the application things of integrals that I feel like we're supposed to be aware of. Area between curves, average value, maybe, volumes of revolution. The rest of it is really just kind of how to integrate things. So the methods of integration. So our methods of integration. Now, there's one, yeah. Okay, so methods of integration. And I'm going to kind of just try and list them by like what you should look for first. So first and foremost, you should try to simplify stuff. Can you simplify it? For example, the integral from, no, I'm making an indefinite integral. The integral of x cubed plus 4x plus 5 over x squared, that can be simplified. It can be rewritten as the integral of x cubed over x squared plus 4x over x squared plus 5 over x squared. And then we can simplify that as the integral of x plus 4 over x, or for 4 times 1 over x, plus 5x to the negative 2. And then you can do the rest. So if you can simplify, great, you should simplify. But a lot of them you won't be able to. So the next thing I'm usually looking for, I'm almost always looking for a u sub. If you can find a u sub, that's what you should do. And the u sub is really available no matter what, right? It can be available if you have a mixture of things or if you don't have a mixture of things. Here are some examples of places where you could use a u sub. The integral of, oh, where'd that problem go there? I had a great problem. That's fine. Of 3x squared plus 12x over x cubed plus 6x squared. There's a great time to use a u sub because the top is exactly the derivative of the bottom. Or the integral of x squared times sine of x cubed. Or literally 1,000 other examples we can come up with, right? There's so many times when u sub is the way to go. Let me just write a few more. The integral of, sure, x to the fourth times e to the negative x to the fifth. That's another good example. Or this is one of the times function I want to make sure I hit here. I guess not. Or the integral of, sure. Sorry, I'm trying to come up with something that's brilliant and I'm failing. Sine of x over 1 plus cosine of x to the third. These are all examples of u substitutions. And I hope, well, we're going to write them down, but I hope that in each of these, the choice of u is fairly obvious. In this problem, in fact, I think all of you should do all of these when you have a minute. Or, 20 minutes, however long it takes. More than a minute, it'll take more than a minute. Here, you should definitely let u equal the bottom. X cubed plus 6x squared. Here, we should be letting u equal what? Anybody? What's a choice whose derivative is also in the integral? Yeah, thank you. Because the derivative is something times x squared. I don't care about the concept, but they still have to work, just work. Here, same idea. Here we should be letting u equal, I would pick negative x to the fifth. Because again, I don't really care about having to adjust for a constant. And finally, over here, this one's probably the strangest of the four. I pick u equal to 1 plus cosine x. All good examples of u substitution. Okay, but sometimes u sub doesn't work. If it's not a u sub, but it's a mixture, so specifically for mixtures, first look for a u sub, because usually a u sub is easier to do. But if it's not a u sub, then we look for integration by parts. This is a reminder, mixture means two types of functions from your list of the four types of things. So you have logs, you have algebraic or any power of x, you have trig, and you have e to the x or exponentials. So a mixture contains typically exactly two of these types, like an e to the x times x cubed, or a natural log of x times x to the fourth, or a trig function times a power of x, or a trig function times e to the x. Those are the typical combinations. So for example, the integral, I'm gonna write down a bunch of them real quick here, of x to the fourth times natural log of x, the integral of x cubed times sine of x, the integral of x squared times e to the x. I just need some dx's here. I have one other example. No, not that example, James. Yeah, I like all these. So in each of these, they would be integration by parts problems, because there's no good choice for u whose du is also there. In the first one here, your u would be, don't get fooled, your u would be the natural log of x. If you're doing integration by parts and there is a logarithm, that is always what you're choosing for u. And then dv is, my favorite two words, the rest. In this case, x to the fourth dx. Here, same deal. So they don't have a logarithm, so now I look for the next thing in my list, which is an algebraic or any power of x. So here my u is going to be x cubed, and my dv is going to be sine x dx. This problem is unfortunate in that it would require integration by parts 3 times. Kind of gross. I will point out that in this case, I would probably encourage you to use tabular if you are allowed to do so. I don't imagine you wouldn't be allowed to do so, but some people are weird sometimes. Same deal here. U would be x squared, dv would be e to the x dx. Again, we could use tabular here, and I probably would, because this is going to require 2 iterations of integration by parts. So we could also use tabular here. What other kinds of things require integration by parts besides these kinds of things? There's a couple things that come to mind. Unfortunately, the integral of just natural log of x, that's also integration by parts, where you let u equal the natural log of x. And what does dv have to be? Right, the rest. I will point out here, right, I'm not writing down the whole thing, right? There's the whole du and v that we need to also find. I'm just not doing it because I know you know how to do it. And then you would use the formula that the integral of your u times dv is equal to u times v minus the integral of v du, which I know you all know, but I'm still saying. Yeah, okay. Sure. All right, a couple things left. Oh, there's that too. Okay, there's more than a couple things left. Oh, okay, yeah. So then I hope this integral doesn't show up on your final, but it could. Ones where you have like e to the x times sine of x, or e to the x times cosine of x. This is that special one where you have to do integration by parts twice. And then you get back the integral you started with and you add it over to the other side. And then add the same integral you started with to both sides. And then divide by whatever the coefficient is. Usually, well, in this very simple example, it's
You're dividing by 2 because you have the integral plus itself. But sometimes you have like coefficients where it's like 1 of this integral plus 9/13 of this integral is going to give you 22/13. Then you multiply both sides by 13/22. It's terrible. Okay. Last couple methods of integration that we have talked about are do I want to do that one first? No. Yeah, sure. Yeah, okay. Sorry, I'm just kind of partial fractions. Again, to use partial fractions, there's a few things that have to be true. You have to have, it has to be rational. The degree on top must be smaller than the degree on the bottom. And finally, you better have something that factors on the bottom. So for example, something like this. Sure, x plus 2 over x times x plus 1 squared. Certainly rational. The degree on top is certainly smaller than the degree on the bottom. The degree on top is 1. The degree on the bottom is 3. And it certainly factors on the bottom. They've already factored it for you. If you encounter an integral that looks like this, where the bottom is already factored, it's a pretty good bet that it is a partial fractions problem. And you should proceed as such. Now, I will point out, no, I won't. Is there time? Oh, sorry. So there's a question here, which I'll answer in a second. Someone would have to be really unkind to give you a problem that was already factored, but wasn't partial fractions. It would feel very misleading to me. I thought of one earlier today. It's like, oh, you could do this, and it'd be really terrible to do that. I don't imagine that's ever going to happen. So if you see something factored like this, I think it's a pretty safe assumption to just use partial fractions. A reminder, in fact, I'm going to change this to x plus 1 to the third. We're not going to do this problem, or at least we're not going to finish it unless we want to. I just want to point out how you do the partial fraction decomposition. So our partial fraction decomposition would be x plus 2 over x times x plus 1 cubed equal to a over x. And we're going to have 3 more terms. You're going to have b over x plus 1 cubed, and then every lesser power of x plus 1. So c over x plus 1 squared plus d over x plus 1. We probably should do it. It's probably good to practice this. Before we go there, someone asked me, is there any time during IVP where you cannot use tabular? And I would say yes, most of the time we cannot use tabular. So going back to the previous page for just a second here, the only types of integrals where you can actually use tabular are where you have x to a power times sine, x to a power times e to the x, or x to a power times cosine. Those are the only 3 types of integrals where you can use tabular. If you want to be slightly more general about it, it doesn't have to be specifically x to a power. It can actually be any polynomial. So if you had something terrible, like, for example, x to the third plus 5x squared plus 2x plus 1 times cosine of x, you could use tabular there as well. It's just, you don't typically see that. It's usually more like this, but again, it could be like that. And again, as a reminder, like, so if I was doing tabular here, the process for doing tabular here would be to write my u as my terrible x cubed plus 5x squared plus 2x plus 1, and then all the derivatives. The kind of feature of tabular method is that when you're doing the tabular method, the u column eventually has to get to 0. Keep taking the derivatives, you eventually have to get to the derivative being 0. If that doesn't happen, you can't be using tabular. So derivative of this is going to be 3x squared plus 10x plus 2. The derivative of that's going to be 6x plus 10. The derivative of that is going to be 6. The derivative of that's going to be 0. And then on the other side here, let me zoom in a bit so you can all see. On the other side, we have our dv, which is just the antiderivative. So you have cosine, and then sine, and then negative cosine, and then negative sine, and then back to cosine. And then it would be
this garbage times sine minus this garbage times negative cosine plus that times negative sine minus that times cosine. And that's the process for tabular. Basically. Yeah. Kind of terrible, but certainly less terrible than actually doing it the long way and writing out integration by parts 3 separate times. So use tabular if permitted. I certainly would recommend it. If permitted and applicable, I should say, right? Don't use tabular when it's not applicable, obviously. Okay, so partial fractions. Yeah, let's go ahead and do this problem because I do think it's good practice. So the first step after you've written the partial fraction decomposition is to multiply both sides by your common denominator. So I'm going to have x times x plus 1 cubed times x plus 2 over x times x plus 1 cubed equal to all of this times x plus 1 cubed. And again, the point of this step is so that we no longer have any denominators. So the left-hand side is just going to be x plus 2 because those cancel each other out. The right-hand side, when you multiply this times a over x, the x's cancel. And you get a times x plus 1 cubed. When you multiply this times that, the x plus 1 cubed cancel, and you get b times x. Here, x plus 1 squared cancels, so you're left with a c times x plus 1 to the first. And here, an x plus 1 cancels, you're left with d times x plus 1 squared. And then, if you're doing it like I think you should be doing it, you're going to use the convenient values of x. One of those convenient values of x is x equal to 0, because it makes all but one of the terms equal to 0 on the right-hand side. If I plug in 0, I get 0 plus 2 equal to a times 0 plus 1 cubed. And I really don't think you should write anything else. B times 0 is 0. C times 0 times whatever is 0. D times 0 times whatever is 0. So I've got a times 1 equal to 2. So a is equal to 2. Great. And then my other convenient value is x equal to what? What makes a lot of other things 0 on the right-hand side? Thank you. Yes. I know you all know. I know you just don't want to say things. All right, so if I plug in -1, on the left-hand side, I get -1 plus 2. On the right-hand side, I get a times 0 plus b times -1 plus c times 0 plus d times 0. So I'm just writing this and I get 1 equal to -b. So -1 is equal to +b. But now I've run out of convenient values. And so I'm going to switch tactics and now start equating coefficients. And I'm going to look for what would be the highest power of x on either side. If I multiplied out the right-hand side, the highest power of x would be x to what number? Show me on your fingers. Multiplied out the right-hand side. Would it be 2, 3, 4, or 5? What's the highest power of x I'm going to get? All right. So if we think about multiplying out x plus 1 cubed, it's x plus 1 times x plus 1 times x plus 1, which will give us an x to the third as the highest power of x. Here you have an x to the first. Here you have an x times x, which is an x to the second. Here you have an x times x squared, which is also an x to the third. But x to the third is definitely the highest degree we have for x. So I'm first going to start with x to the third. Why am I starting with the highest power? The reason I'm starting with the highest power is because there's going to be the least number of terms I have to deal with, which means it's going to be the easiest to solve for the things that are still left. On the left-hand side, I have 0x cubed. On the right-hand side, if I multiply this out, x plus 1 cubed, and then I know it's been a while, x plus 1 cubed is x cubed plus 3x squared plus 3x plus 1. X plus 1 squared is x squared plus 2x plus 1. So when I multiply the right-hand side, I get a times x cubed. I don't have a b times x cubed. I don't have a c times x cubed, but I do have a d times x squared, which would be a d times x cubed. Or in other words, 0 is equal to a plus D. But we know that A is 2, so D had better be -2. And lastly, now I'm going to look at the next highest power of x, which is x to the second. So now x to the second is a little bit dicier. I still have 0x² on the left-hand side. On the right-hand side, I would have an a times 3 times x². I'd have a 3ax². I still don't have a b, right? B times x² doesn't exist. I would have a c times x². C times x is c times x². And I would have a d times 2x² because this dx distributes to that second term. And I have 2x times d, which is 2dx². Getting rid of the x², I have 0 equal to 3 times a is 6. C is what I'm trying to figure out. And 2 times d is -4. So it looks like 6 minus 4 is 2. 2 plus c equals 0. So c also equals -2. And then you would go back and you'd actually do the integral. So the integral would end up equaling the integral of 2 over x. Now watch how I write this next part. I'm not going to write b over x plus 1 cubed. I'm going to write b, which is -1, times x plus 1 to the -3rd. And c, which is -2, times x plus 1 to the -2. And then I am going to write -2 over x plus 1. Because I know that if I'm dividing by something that's linear, I'm going to need a natural log as my result. Whereas if I'm dividing by something that's a higher power of a linear thing, I'm using the reverse power rule. So this is going to end up equaling 2 natural log of the absolute value of x minus x plus 1 to the -2 divided by -2. I know this is getting, I'm sorry I haven't squeezed in this in here. Well, I'm fully capable of doing it some other way, but I'm doing it this way. -2 times x plus 1 to the that should be a -2 there. Sorry about that. The -1 over -1. And then finally, -2 times the natural log of the absolute value of x plus 1. Let's see. So there's a partial fractions problem. I would imagine you'll see one that has a repeated linear factor so that you have to do this multiple things over here kind of deal. Okay. There was something else that was on my mind. Oh yeah. Sure. So maybe the last thing, which I feel like really isn't a separate thing, but it feels like it to people for some reason, trig integrals. So most of the time when you see trig integrals, it's still just a u substitution. Most trig integrals you're going to see are going to be u subs. So talk about trig integrals for just a moment. Yeah, I'm going to write a few and we're talking about what we choose for you, and then I'll leave you to do them on your own. So I'm going to have, yeah, let's do that. Let's say the integral of sine to the 5th x. Yeah, cosine x dx. The integral of sine x over cosine cubed x dx. The integral of secant to the 4th x times tangent x dx. Was that a bad choice? No, it's fine. The integral secant to the 4th x. Nope, I don't want that. Secant squared x times tangent cubed x dx. Those all seem not too terrible. Okay, each of these trig integrals is a u sub. And your job is to pick the right trig function for you. And your choice should always be single trig function, meaning u equals sine of x, or u equals cosine of x, or u equals secant of x, or u equals tangent of x. Shouldn't be picking secant to a power, or sine to a power, or cosine to a power. Just straight up, regular, single trig function. So, in this one here, we should be letting u equal sine of x. So that your du is cosine of x dx, and it exactly gets soaked up by right there. So you're left with u to the 5th. Great. I should say
you're left with u to the fifth d.
There's your du, there's your u to the fifth. Okay, in the same sort of way, what seems like the plausible choice for you in this example? Sine or cosine? So if we pick u equal to sine, what's our du going to be? No, it is cosine. It's still cosine. So, right, if u is sine, the derivative is always cosine. But in this example, if u is sine, du being cosine of x times dx is problematic because I don't have cosine of x times dx. All those cosines are trapped in the denominator. So here I'm going to make the other choice, which is to let u equal cosine of x, because then the du is going to be essentially sine of x times dx. Yes, it is negative, and that's often the place where people get caught like, oh, I don't want that negative sign. The negative sign is not that important, right? Or I should say the negative sign is manageable. So don't worry about the negative. We can always adjust for that. You want to pick the thing so that the derivative is exactly showing up as closely as possible. So then I would say that negative du is positive sine of x dx. And then this is looking like negative du on top, u cubed on the bottom. So if you wanted to rewrite this, it would look like the integral of negative du over u cubed, or I would maybe write it as negative the integral of 1 over u cubed du, or even as negative integral of u to the negative third du. You're done. I feel like the sine and cosine ones are usually easier in that it's almost always going to be that you're choosing the one that's raised to a power, and the one that's only occurring to a 1 power should be not your choice, because it's going to be the du part. For secant and tangent, it's a little bit more challenging. You want to make a choice for u so that the other one gets soaked up by your du. So here, I don't want to pick u equal to tangent. If I pick u equal to tangent, my du is going to be secant squared, but there's going to be secant left over, which is problematic. I definitely want to pick u equal to secant here. My du is going to be secant of x times tangent of x dx, which will take care of the tangent and also one of the secants. So this is a good example of where you definitely want to make sure you take care of du first. Because if you did, here's the wrong thing, which I'm not going to write down. You could start off by saying, oh, secant to the fourth is going to become u to the fourth. And that's not going to help us. Because before we can do that, we need to pull one of those secants out to use for our du. So we should definitely rewrite this as the integral of secant cubed x times secant x times tangent x dx. And then it's a little more obvious that, oh yeah, the secant x tangent x dx is our du, and the secant cubed is our u cubed. And that's straightforward. And then oppositely over here, in this example, this is where we should let u equal tangent. Let u equal tangent of x over here, then our du is exactly secant squared x dx. So this can be rewritten as the integral of tangent cubed x times secant squared x dx. And there's your du. And there's your u cubed. So that's my quick rundown on trig integrals. Most of the time they end up being, like if it's, I should say, if it's just trig, right? You don't have other things in there. Most of the time it just ends up being some sort of u substitution. It doesn't mean it couldn't be something else, but it's often. All right, so that's most of the methods of integration. There's still a couple other things that we should talk about that I haven't mentioned yet. One of them being improper integrals. And I don't remember, for Tav's class, did we do both types or did we do just the ones that went to infinity? Sure, fair question. So we definitely did ones like this where it was like the integral from 2 to infinity of e to the negative x, or the integral from 1 to infinity of 1 over x dx, for example. Those are improper because we have an infinity. But there's also the other, so I guess this is type 1, and the type 2 ones are ones like this, the integral from 2 to, sorry, brain. 2 to 11 of 1 over the square root of x minus 2. It's improper because the function is undefined somewhere on the interval of integration. Did we do ones like that? Okay, I don't think we did. I don't know if they did them in Lee's class or not, but I'm pretty sure we didn't do them in Tab's class. So either way, right, you're still right for these improper integrals. You're going to replace your place of improperness, infinity, or if it was this problem, 2, with a letter like A or B. So for this one here, I would rewrite this as the limit as b approaches infinity of the integral from 2 to b of e to the negative x. And then we just go along our merry way. We integrate as usual. Just keeping the limit out in front the whole time. You write it down, but just kind of ignore it until the very end. We integrate e to the negative x. We get negative e to the negative x, or e to the negative x divided by -1. Same difference. From 2 to b. Then we plug in our limits of integration. We still have the limit out in front. We get negative e to the negative b minus negative e to the negative 2. At this point is where I would rewrite things so that I won't say positive powers. What I want to happen is that when I plug in my limit, infinity in this case, I really want to end up with powers that are positive infinities, not negative infinities, because it's easier for me to think of. If you're comfortable saying e to the negative infinity is 0, good for you. I am not, for whatever reason. I would much rather write this as the limit as b goes to infinity of -1 over e to the positive b plus, you can write this as e to the negative 2 or 1 over e squared. Either way is fine. And now I say, oh, great. B is going to infinity. E to the infinity is super big as well. And 1 over something very large is going to be very, very small. Goes to 0. So we get 0 plus 1 over e squared, which is 1 over e squared. And you should write down somewhere the words that this improper integral does what? Verges, some sort of verges. What's the word I'm looking for? Does it converge or does it diverge? I'm not asking to like make you think you did it wrong. I'm really just asking. Those are the two things. Well, this one is definitely convergent because we got a real finite number as the integral. So this is going to be convergent or converges, either way. Or sometimes the interval diverges. For example, I don't love this example because this is too easy. Like this is like the base case that everyone gives as an example when they talk about this. So let's look at a different example. If we got time. Okay. So an example you could maybe see would be something like, do that. The integral from negative infinity to infinity of, sure. I don't love that actually. Yeah, let's do that. Ooh, yeah, sure. Sorry. X squared e to the x cubed. That seems really terrible, James. Okay. There's two reasons this is terrible. One is both of your endpoints are problems, so you have to break the integral up. You're required to split up any integral with more than one problem into separate integrals where each integral only has one problematic point. Where are we going to break it up at? Doesn't really matter, but the common choice would be 0. The middle. We're going to do the integral from negative infinity to 0 of x squared e to the x cubed plus the integral from 0 to infinity of x squared e to the x cubed. Okay, so here's what I would say. You should try to pick the integral that you think might diverge. One of these, I'm more confident diverges than the other one. I'm pretty sure that this one's going to diverge because x squared and e to the x cubed are both getting infinitely large as x gets infinitely large. On the other hand, I'm not as confident about this one because even though x squared does get infinitely large and x goes to negative infinity because negative infinity squared is positive infinity, e to the negative infinity cubed goes to 0. So I don't know if this one's going to diverge or converge, but I'm pretty sure that this one's going to diverge. And if one of them diverges, the whole thing diverges and you don't have to check the other one. So if you have something like this where you have to break it up into more than one piece,
try to identify the piece that you think is going to diverge. It might not. They might both converge. That's fine. But if you have intuition about one of them maybe being divergent, pick that one first. You're going to do less work. So let's look at this one. The integral from, let's write it as the limit as b goes to infinity of the integral from 0 to b of x squared e to the x cubed. I really don't like doing a u sub or really anything complicated when I have all this other machinery over here. So off to the side, I'm going to do the indefinite integral of x squared e to the x cubed with a u sub. U is x cubed, du is 3x squared, dx, 1/3 du is equal to x squared dx. So this is going to become the integral of, there's my 1/3 du, and there's my e to the u, which is going to be 1/3 e to the u, which is 1/3 e to the x cubed. Which seems reasonable. If we take the derivative of that, the derivative of 1/3 e to the stuff would be 1/3 e to the stuff times the derivative of the stuff, which would be 1/3 e to the x cubed times 3x squared, and the 3's cancel, and you get x squared e to the x cubed. Awesome. So then we have the integral right there. It's 1/3 e to the x cubed from 0 to b. And yeah, this is looking pretty strongly like it's going to diverge. Because if we plug in b, you have 1/3 e to the b cubed minus 1/3 e to the 0. And certainly as b goes to infinity, b cubed gets infinitely large, and e to something that's infinitely large is also infinitely large. So you're definitely getting infinity minus 1/3, which is infinity. So we say this diverges. It's a lot of things. Not an unreasonable amount of things, but just like there's a lot of topics that show up on your final. Okay. You might have to use an integration table. I don't feel like there's anything I can really say about that other than try to do your best at identifying which part of the table you should be looking at. So that you, and I don't remember how it's broken up exactly, but like broken up to like logs, trig, and then various forms of ax plus b or ax squared plus b or the square root of ax squared plus b. But definitely like whether there's a square root or not, whether there's an x squared or an x or whatever, that's usually kind of broken up into different things. So try your best to identify the thing. Sometimes you might have to do a u sub before you can identify the thing. I recommend actually doing the u sub and writing the new thing in terms of u and then being like, okay, where is it on the table? But I don't have a lot of good advice other than try your best to look carefully at the table if you have one. I don't know if you will have one on your exam. I imagine Tab will give you one because it seems like he cares about that. I don't know what Lee feels about that. And then finally, we have like the chapter 9 stuff. So we have all of the, oh, that's not true. I forgot about the mid. So there's also the estimation stuff. I'm running out of time, clearly. So the estimation stuff, we have the trapezoid. Did we talk about midpoint as well? I don't remember if we did midpoint or not. Yeah, I know this trapezoid. Trapezoid, I feel like, is the one that Tavernet is going to talk about. So trapezoid. So if you have some interval from A to B, yeah, sure. Let me just draw it this way. From A to B, and you're breaking up into n subintervals. So A is your x sub 0, and you have x sub 1, x sub 2, all the way to B being x sub n. Here's the formula that you just need to know. Your trapezoidal estimate using n subintervals, that's what the n is for, is going to be your delta x over 2, and then it's this 1, 2, 2, 2, 2, 2, 2, 2, 2, 1 pattern. So it's 1 times f of x sub 0, and then it's 2 times all the middle ones. So f of x1, f of x2, all the way to the second to last one, which is x sub n minus 1. And then finally, it's 1 times the very last one, f of x sub n. Where delta x is b minus a divided by n, just your total length divided by the numbers of intervals. And x sub 0 is a, x sub 1 is
a plus delta x, x sub 2 is a plus 2 times delta x, and so on and so on and so on. Each x sub whatever, just adding on another delta x to get there. Usually you don't need to know the general formula for this because your examples are like n equals 4 or n equals 6, and it's kind of over before you know it. And then there's the error formula. Which is that, I remember the error formula, the absolute value of your error is less than or equal to, do I remember? It's, oh my goodness, it's b minus a cubed over 12n squared times the maximum of the absolute value of the second derivative over the interval. And almost always you're estimating this, right? You're looking at your second derivative, you're trying to figure out, okay, most of the time, not all of the time, but most of the time, does my left endpoint make it as big as possible, or does my right endpoint make it as big as possible? The only time I would say that's not the case is if your function happens to have like sines and cosines in it, and they're like, okay, each sine and cosine is less than or equal to 1, and then just kind of see what you got. I know that Lee's class did talk about Simpson's rule, which is just another type of thing. That is something else that you should be aware of if you're in Lee's class. I don't feel like it's super helpful to write it down because it's just another formula. But if you have questions about Simpson's rule from Lee's class, come see me. I'm happy to talk about it. And then lastly, these are all the things you're responsible for now. Lastly, so I don't say that to make you worried. I don't think you should be worried. I think you all know what you're up against, right? Not that it's like a battle, but like just you've learned the material, right? You know what you're doing. You've seen all this stuff. It's a lot of things to be aware of, but it's also very, very manageable. I know you're capable of doing it. The last list of things is just the stats and probability stuff. And I would kind of boil it down to the mean. So basically for discrete, we have that all the probabilities have to add up to 1. So I would write this as the sum of the probabilities have to add up to 1. Or if you like, probability of the first thing plus the probability of the second thing until you're done with all the things has to add up to 1. The expected value is just each value multiplied by its probability. So x1 times p of x1 plus x2 times p of x2, and so on and so on and so on, which again, we often write as the sum of x sub I times p of x sub I. And I would always use the alternative version of the variance formula. The variance formula is just the, sure, I would write it as the sum of xi squared times p of xi minus whatever your mean squared is. That's the nicer version of the formula, which we typically use more in the continuous version. And then the standard deviation is the square root of the variance. And then for continuous, it's the same formulas, just with integrals instead of summations. So for continuous, the integral over your interval of your PDF has to equal 1. Often there'll be a question like, let's say your PDF is k times some function, find the value of k that actually makes it a PDF by integrating the thing, setting it equal to 1, and then solving for k. And then we have the same sorts of formulas. The expected value is the integral over your interval of x times your PDF, just like it was here. It was x times your probability. The variance is equal to the integral from a to b of x squared times your function dx minus your mean squared. And just to make sure everyone's on the same page here, I'm using mean and expected value interchangeably. Expected value of x is another way of writing the mean. Same deal here. So I'm writing mu squared there when I could be writing that squared if you prefer. And just like before, the standard deviation is the square root of the variance. I know it's 11:51. I just want to say one more thing, two more things. You find the median. I'm gonna call M by setting the integral from A to M of your PDF equal to 1/2, or by setting your integral from M to B of your PDF equal to 1/2, and then solving for M. Usually, the first version is easier, but I could see someone coming up with something where doing it this way was easier because they wanted to make it easier that way. But right, so you like, so if your interval is from like 0 to 5, you're gonna do the integral from 0 to M equal to 1/2, or the integral from M to 5 equal to 1/2, and then try to solve that for M. And then really lastly, the other thing I think of all the special probability density functions, I feel like the one you might be asked about would be the exponential one. So I'll just remind you of the special exponential PDF, which looks like f of x equal to a times e to the negative. Is that how I wrote it before? I don't remember if I wrote it as a or 1 over a before. I think I wrote it as 1 over a. Yeah. Sorry, there's like 5 good ways to do it. There's 2 good ways to do it. So I think we normally write it as f of x equal to 1 over a times e to the negative 1 over a times x. If you write it that way, then the expected value is equal to a, and the standard deviation is also equal to a, which would imply that the variance is a squared. Oh, I forgot one thing. That's on the interval from 0 to infinity. I did notice on Lee's exam, final exam from 2-3 years ago, he did ask people to calculate the expected value and the variance of something like this, which I think the variance is kind of, well, so actually, I don't know if he certainly gave enough space on the page to calculate the thing. I don't think his intention was for you just to be like, oh, the answer is 5 squared or whatever the a value was. So, but I don't know what Tavernetti's expectation around this is. You might. So if you know what he expects, I feel like his tests are usually pretty clear around his expectations. Like he's going to write what he wants you to do. So if you have to find the variance of, for example, if my PDF was 5e to the negative 5x on the interval from 0 to infinity, the expected value of x is going to be 1/5. The reciprocal of whatever that number is over there. I could have written this like this. I could have written it as 1 over 1/5. No one's going to write it that way. I could have written this top part as negative 1 over 1/5 to more strongly show you what a is, but that's the idea. And then the variance would be 1 over 25. I could see asking a question like that, where they give you this and they're like, okay, what's the expected value? What's the variance? And they give you like a tiny amount of space, meaning you're not, right? When people give you not very much space, they're trying to tell you something. They're trying to tell you it shouldn't take that much work to figure it out. If you're doing a lot of work, you're like, oh, maybe there's something weird here or something special. All right, that's all I've got. Good luck on your finals. I think you'll all do fine. I'll see you next quarter for 16C if you're taking it. And next week, all the specialists are in drop-in Monday through Thursday from 10 to, I think we're there 10 to 3 or 10 to 4. So it won't always be me, but I'm there I'm really like 4 hours a day. So if you're looking for me, you can find me. I guess I'll post it on Canvas too. I'll post when I'm there on Canvas and then when everyone's there. But I'll be there most days from like 10 to noon and 1 to 3. Except I think Monday I'm only there 10 to 11 or 1 to 3. So yeah. All right. It's been fun. Hope you all do well.